Okay, thank you for that introduction, Erin, and thank you for having me back. It's been, I believe, 4 years since my last trip home to the mothership, so to speak. Today I'm going to be talking about the first of a couple of papers on a new subject for me, namely the sun at GeV energy levels. So this is work in collaboration with a bunch of OSU and ex-OSU people. So Karsten Roth, who was a CCAP senior fellow for 5 years, but is now an assistant professor at Sungkyunkwan University in Korea. John Beacom at OSU, and the man who made it all happen, Kenny Eng, who is currently a grad student at OSU. He is on the job market this fall, and he is amazing. Like, none of the stuff that I'm going to show you would have been possible with pretty much any other person working on the subject other than him. Okay, so I recently had a baby at the very end of December, just barely being a 2014 tax write-off. And so this has launched me into the world of children's literature, which I have to say very much promotes the anthropic view of the universe. The first book that we read with him, The Sun Shines All for You. No, the sun keeps shining regardless of whether the baby's there to read this book or not. But it is true that the sun, as our nearest star, is really our touchstone for a lot of both fundamental physics and astrophysics. So the sun, our nearest star, is only microparsecs away, so we can really study the heck out of it. So this is an image of the sun taken with various instruments on the Solar Dynamics Observatory, looking at the sun in a variety of wavelengths from optical up to X-ray. You can see all sorts of very interesting features. It helps that because we're only microparsecs away, 1 arc second is of order the distance from here to Trenton. So you can see a lot of stuff on the sun. So we can really study it very well with photons. We can also study the sun with neutrinos. So this is an image of the sun from the Super Kamiokande neutrino experiment. So as opposed to this previous slide where we can resolve things on sort of like arc-second scales, this image is sort of like 90 degrees on the side. So the resolution is not great. But yet, the sun is an extended source of neutrinos that we can see. And in fact, we can now actually measure neutrino energy spectra from the sun, which tells us very nicely that the sun works as we think it works. So that's a subject that hits fairly close to home here at IAS. But the other thing that we can probe the sun with is cosmic rays. So the sun is a prodigious producer of lower energy cosmic rays. So cosmic rays stream out of the sun and entrain magnetic fields, do all sorts of interesting things. And those charged particles interact with us. They distort the Earth's magnetic field and produce pretty aurorae, and also occasionally also disrupt our communications system. Okay, so we can probe the sun using really this multi-messenger approach, and we can really study the heck out of it. We can learn a lot of interesting things about the astrophysics of stars, but also fundamental physics. So let me remind you that the element helium derives its name from helios, the Greek word for sun, and that's because during the 1868 solar eclipse, people were able to probe the chromosphere and corona, and there was this interesting line feature at about 5,700 angstroms, really 57, I think 86, which is a helium line. So the sun, so that eclipse is great. This the gentleman scientists at the time discovered the chromosphere and corona, but also discovered helium. Through a combination of optical observations as well as neutrinos, we know that our solar models work really, really well, which is important when we're trying to study other stars. So this is just a nice image of what the sun's convective cells look like in a simulation. And the neutrinos let us know that basically nuclear fusion proceeds the center of the sun to power the sun exactly as we think it does. So through this combination, we've learned that our solar models are great, and we have learned that neutrinos oscillate, or in other words, as I like to think about it, astrophysicists are not idiots. When we predict some number of neutrinos, they must be there, even if they have oscillated into species that we have a harder time detecting. Okay, so fundamental astrophysics as well as physics. We also can see that the sun is very active, and there's a lot of high energy stuff going on. So the sun magnetic field is powered by a dynamo, and through convection, the convective layer and the MHD that goes on outside of it, we can see all of these interesting magnetic features. It's a very dynamic place. So here's an image of what the sort of large-scale field of the sun looks like, as well as sort of what some of the smaller scale fields look like. So we've learned something about how the sun sort of operates, but the sun is also a fascinating laboratory for MHD. Okay, so what I want to talk to you today about is the sun at GeV. Basically, what can we learn, both in terms of sort of fundamental physics and astrophysics, by looking at the sun in the GeV energy range. So the outline for the rest of this talk is going to be, first of all, I'm going to sort of outline what sort of things that we could learn. Then I'm going to talk about some of the data that exist where we can already start learning some interesting stuff about the sun at these wavelengths. Going to talk specifically about, and this will become more clear soon, what the implications of our observations are for basically cosmic ray propagation in the inner solar system. And we'll have some, I'll at the end discuss some implications for detection both in gamma rays and neutrinos at higher energy levels. So this is going to be something that is going to be of high interest to our experimental colleagues on HAWK and IceCube. Okay, so let me delve into what we can learn by observing the sun in the GeV energy range. Okay, let me pause. Are there any questions so far, or no, we're still good? Better than at my thesis defense, where it took me a half hour to get out of slide 3, seemingly, of my defense. Okay, so what can we learn about the sun at GeV? So one thing that I should say, first of all, that we learn about non-thermal processes on the sun. So even the corona of the sun, which is a couple million keV, that typical energy is sort of, 2 million Kelvin, that energy is about a keV. So that's 6 orders of magnitude short of a GeV. So the things that we learn about are really non-thermal processes in the sun. So one of the non-thermal things that we learn about is dark matter. So maybe some of you who've known me for a while are wondering, why is this person who mostly thinks about dark matter, why is she giving a talk about the sun? And that's because one of the things which I also investigated in my PhD thesis is sort of what you can learn by looking at the sun about dark matter. So how does this work? So the solar system basically is bathed in dark matter from our fluffy Milky Way dark matter halo. And occasionally one of those dark matter particles, here labeled chi, runs into the sun and whacks into a solar nucleus, deposits some energy, and then sort of like orbits around and eventually, scatters again and again until you form this dense little dark matter core in the sun. The dark matter particles, we believe, or we strongly hope, are self-annihilating. And then those dark matter particles annihilate, produce a bunch of standard model crap, some of which is neutrinos, and those neutrinos are things that we can detect. So by looking at the sun in sort of GeV to TeV neutrinos, we can sort of probe the dark matter's cross-section with normal matter. So in particular, the annihilation rate is almost certainly governed by just the capture rate of dark matter in the sun, which means that we set a limit on the elastic scattering cross-section. And since the sun is basically a gigantic ball of protons, the thing that we're most sensitive to is the spin-dependent WIMP, or rather dark matter particle proton scattering cross-section. So this is a plot of cross-section on this axis and dark matter particle mass on this axis, sort of GeV. And these experiments, so Super K and Antares, Bach Sun, and IceCube are all neutrino experiments. And the limits that they can set on this cross-section are much better than current limits from direct detection experiments. So these are direct detection experiments or dark matter experiments that are essentially big vats of nuclei buried deep under a mountain or underground on Earth, and you just wait for a galactic dark matter particle to whack into one of your nuclei. So anyway, the sun right now sets the best limits for this type of cross-section. Some of them do, yes. They lose energy, yeah, because they're hitting. Yes, yeah. Okay. Any more questions, or I saw another hint.
You need some sort of specific model for how the winds are captured by the sun and the rate at which that happens.
Yes.
And that must all be tied into the cross-section.
Right. So what it depends on is the cross-section. You need the velocity distribution of particles. So it's much easier to capture something that's moving at 100 kilometers a second than 1,000 kilometers per second. Yeah. So those are the main inputs. You have the particle input as well as the astrophysical input. Yep.
Most of the annihilation occurs well within the solar photosphere?
Yes. Yeah. So usually it's within the inner 0.05 solar radius. That it depends a little bit on the WIMP mass and whether it interacts more strongly with hydrogen or helium. But yeah, basically, it's really within the very inner part of the sun. Okay, so that's how I got sort of hooked onto what I'm going to be talking to you about later, the story of which I will tell in more detail. But basically, how I got sort of hooked on the sun is through its use as a dark matter experiment. There are also other cool things that you can learn about. So this is a fundamental physics application. Let me talk about an astrophysics application. So you can learn about solar flares. So the sun is very active, especially now we're in sort of the active phase of the solar cycle. And occasionally you see bright flashes of light from the sun. So these are sometimes associated with what are called coronal mass ejections. So in addition to this very bright flash of light, you also see bursts of charged particles run at us. And one interesting thing that you can do at GeV is you can learn something about the acceleration process of those charged particles. So this is the brightest flare observed by the Fermi LAT experiment. So Fermi is a space-based gamma ray experiment, which I'll be talking more length about later. But this is the sun, or sorry, this is how the sky looked the day before this flare, and this is how the sky looked the day of the flare. So, so the sun was extremely bright in gamma rays, up to about 4 GeV. And the Fermi Lat team basically looked at the spectral evolution of the flare in GeV. So this is a couple hours after peak, 3.5 and 5 hours, and the whole flare lasted about 20 hours. What they found is that the spectrum here, the energy spectrum, looked really sort of pionic in origin, and it lasted a super long time. So they posited that these charged particles are sort of continuously accelerated in the corona of the sun, and then they whack into the solar atmosphere, shower, and produce a lot of pions, and then we see this nice pion bump in the spectrum. So that's a nice bit of astrophysics, of learning how particles are accelerated in the very complicated magnetic environment of the sun. The thing, though, that I'm going to spend the rest of this talk describing is basically how we can learn about charged particle propagation in the inner solar system by looking at the sun in GeV. Okay, so there are actually two distinct signals, or two components. We have an inverse Compton halo, and we have a solar disk component. And I'll be describing basically a little bit of the theory behind these two signals and then observations after that. Okay, so the first thing that we can look for is inverse Compton. Basically, cosmic ray electrons interact with solar photons, upscatter them to GeV. And so basically, the signal that you get depends somewhat on how charged particles actually propagate in the inner solar system, because you'd like to have lots of cosmic ray electrons sort of in the denser photon field of the sun. But the key signatures of this sort of interaction are that we should only see photons, okay, because it's cosmic ray electrons hitting sort of EV scale photons, so we should really only see photons. We expect for this signal to be extended because there are lots of cosmic ray electrons in the inner solar system. There are also a lot of solar photons, so this should be an extended source. And we expect that the spectrum should peak in the sort of GeV range. So there's the way you can think about this in sort of an order of magnitude sense is that, for reasons that I'll show in a little bit, the electron spectrum is sort of peaked around sort of GeV energies. And so the gamma factor for inverse, when you consider inverse Compton, the energy of the outgoing photon sort of goes as the electron gamma factor square times the photon that you hit. So gamma here for the typical electron near the peak of the spectrum is sort of order 10 to the 4. Solar photons you can imagine as being sort of 10 EV, and so the typical energy that you expect to get from this inverse Compton halo is sort of GeV range.
Why is the solar photon changing?
It's just sort of order of magnitude. It's really more of order EVs, but within sort of factors of a couple, gamma is also probably more like a couple thousand instead of, anyways, order of magnitude, we're sort of sitting in GeV range. Okay, so the second component that you could get from cosmic ray interactions with the sun is in the solar disk. So basically the story here, the simple story, is that cosmic ray hadrons, namely, or mostly protons, come in and they whack into solar nuclei and they shower. So if the proton energy is super high, then if you hit sort of the main body of the sun, then the whole shower propagates into the center of the sun and you never see gamma rays. But you can see neutrinos because you produce these pion showers and you get neutral pions as well as charged pions. So the charged pions decay to neutrinos. So you do get neutrinos out. If the cosmic ray hits sort of in the limb of the sun, then you can get some gammas out as well as neutrinos, as long as the column you're looking at is sufficiently thin. And I'll be talking about this more later. At lower energies, though, the cosmic rays interact significantly with the interplanetary magnetic fields as well as the solar magnetic field, sort of from the photosphere up through the corona. And so those particles dance around and sometimes get sent back outward through the sun. They plunge down a flux tube and get bounced back, and then you can get some gammas from that, and you always get neutrinos. All right, so let me walk you through again how this works. Step one is you have cosmic ray hadrons, again mostly protons, sort of interacting with the plasma filling the inner solar system, mostly for the energies that we care about. What's going on is that those cosmic rays are sort of spiraling around the mean large-scale field in the inner solar system, but they also scatter off of magnetic irregularities, giving you sort of a diffusion. So the gyro radius is much smaller than the radius of the sun. Yeah. Okay. And so we know that there has to be some significant diffusion of cosmic rays in the inner solar system, because if you look at the energy spectrum of protons sort of at the Earth's position, that energy spectrum actually changes with the solar cycle. So the sun was very quiet in sort of 2008, 2009, which is where the proton spectrum at Earth sort of peaked. And as we went back earlier in time, this is a plot from a Pamela paper. Pamela is a satellite cosmic ray experiment. If we were sitting just in the local interstellar space, this proton spectrum would just continue to go up like this. And so the fact that we see this turnover tells us that charged particles of this energy are having a hard time diffusing into the heliosphere. Okay, so we know that, particles diffuse around, and that the magnetic fields in the inner solar system actually matter, and outer solar system matter a lot. The second step that you have to think about when you're considering how these cosmic ray hadrons interact is that you have to consider what happens as these cosmic rays get close to the corona and then the chromosphere and photosphere of the sun. So the magnetic fields go up, way up in sort of the edges of convection zones. And cosmic rays basically get mirrored out of these flux tubes before they can get too far. Basically, in order to conserve magnetic flux, like those particles just cannot go super deep in. Okay, so we've got cosmic rays sort of propagating into the solar system and then into the sun, possibly bouncing out. And then some of them interact and they shower. And the sort of main physical generators of things that we want to see are neutral pions that decay to photons. Charged pions decay to neutrinos, but you can also, through the charged leptons here, initiate electromagnetic cascades if your column is thick enough. So you can get photons out either by neutral pions or by electromagnetic cascades, and you get neutrinos out from just basically charged pion decay. Okay, so that's how you can generate lots of GeV photons and neutrinos. No, so these are like galactic cosmic rays. Yeah. Yes. So, okay. So actually figuring out what you expect for a signal is a little more complicated than the inverse Compton. So inverse Compton is pretty simple. We know what photons the sun produces. We also have a reasonably good handle on what the electron galactic cosmic ray spectrum looks like, and that's really all you need. For the solar disk part, a lot depends on the magnetic fields, and basically where particles can actually hit the sun and shower. So the intuition for what we expect is a little, I mean, you can get some intuition for what we expect, but the prediction is not as, I would say, airtight as for the inverse Compton component. So one thing that we can probably say, is that the spectrum should be pretty pion dominated. That is certainly true for the neutrinos. But even for the photons, it's probably pion dominated because basically the electromagnetic showering length has a similar optical depth to protons hitting other protons. And so if you want to get gamma rays out of your system, the column cannot be too thick, otherwise you sort of absorb everything, which really limits the electromagnetic showering component. So in order for the column to be thin enough that you actually get gammas out, you're not going to initiate showers. You're only going to really mostly see the pion contribution. So probably the spectrum should be pion dominated. Also, probably not all the protons scatter would be our intuition, because those a lot of the cosmic rays get mirrored out of the sun at fairly low columns, so they have a pretty low probability of scattering. However, the overall normalization in spectrum probably depends on just how those charged particles can propagate in the inner solar system and in the sun, and that is a large source of uncertainty, which I'll talk about in a minute. And then, finally, you should get neutrinos as well as photons. So this leads me to the anecdote of how I actually got involved in this in the first place. So one of the papers that I submitted as part of my thesis was looking at dark matter annihilation in the sun. So I get back the most useful referee report I've ever gotten in my life, which said, oh, this is very interesting, but have you considered this foreground of cosmic ray interactions in the sun? Is that something that you have to worry about for your signal? And so I dug through the literature and discovered that there were very few calculations, and moreover, we were soon going to get Fermi data and could maybe actually try to empirically determine what our neutrino foreground for dark matter searches should be.
Then if the cosmic rays come in and reflect, and on the way out they produce the showers?
Yes, or if they're on their way in and the charged particles in the shower can be deflected up, can be mirrored out as well. Yeah.
Neutrino experiments have spatial resolution. These should be the size of the disk.
Yes.
The dark matter annihilation should be right in the center.
Yeah, so they don't have the resolution at sort of the GeV to TeV energies that are most interesting for dark matter searches, and that's just due to kinematics more than anything else, that if you have a neutrino coming in and hitting something, the outgoing muon, if you want to get a track, which is relevant for IceCube, there's some kinematic angle that is large compared to the size of the sun.
The limb effect, because there's so much along the pathway through which they can interact on the limb.
Yeah, so I'll talk a little bit about the limb in a bit. But yeah, so up until this year, there have not ever been a limb calculation. So I'll show you the first ever limb calculation in just a little bit. We are also coming to that, basically, instantly. Okay, so I just wanted to give a little bit of the sort of theory behind how you make the sun glow in GeV. So basically, inverse Compton, solar disk, inverse Compton, the theory, there are fewer uncertainties. For the disk, as I'll show you, there are large uncertainties. So the way you constrain the uncertainties most prominently, which I'll get into more very soon, this thing about charged particle propagations, what you really want is some data and try to constrain these uncertainties with data. Let me just skip that. Let's go to the data. All right, so okay, so the sun was only marginally detected with egret. So egret was a gamma ray satellite from the 90s, or an instrument in the 90s. So the sun was, you can see here instead of 100 to 300 MeV sort of seen, these pixels are smoothed on sort of 3-degree scales. Yeah. So basically, because the pointing is, or rather the PSF is so huge, you're really, dominated by diffuse backgrounds. And a lot of things that we now know are point sources would then, in the egret era, have been contributing to the diffuse background. They're about, I guess, sorry, the pixels aren't smooth to 3 degrees, but this whole image is about 5 degrees on the side. So, but still you can tell by the scale of the features that the PSF is not wonderful here. Okay, so we have a marginal detection of the sun in GeV photons with egret, but in the Fermi era, even just basically within days, they were able to see the sun. So this is an image of the sun in photons above 300 MeV from the Fermi-LAT collaboration's 18-month paper. So this is from 2011. This is a nice image of the LAT up here, the Fermi satellite, and it's still running. It should be running at least through 2016. They're going up for senior review again, and they hope to be extended to a 10-year mission. So Fermi is it's chugging along, doing great science, and has now seen the sun. Even at this time, they were claiming that they had detected the sun to like 40 sigma or something. So, the sun is there, the quiet sun. Oh, yes, sorry. That is an important point. So this is what the way we estimate, the way the Fermi team estimated, and the way we in our analysis estimate the background is basically by having a lot of fake suns. So we put a bunch of fake suns along the ecliptic, but at different phases from our real sun, and basically perform the same analysis on the fake sun as we do on the real sun, right, to estimate the backgrounds. Because you trace out the same path as the sun, so anything that for the background, yeah. Okay, so this is the Fermi team's result, where they, so this is again looking at the angular spectrum, or the angular distribution of photons from the sun for photon energies above 300 MeV. And they find both in inverse Compton, which is this line here, and disk component, which is great. So the disk component is narrow. Here it's sort of wider than sort of the size of the sun, because you're really dominated here by these 300 MeV photons, which have a large PSF compared to higher energies. So once you get to about a GeV, the PSF drops to only slightly bigger than the size of the sun. The interesting thing, though, comes in looking at the energy spectra. So on the left, I'm showing the energy spectrum of the inverse Compton component. So the two sets of lines here, this is within 5 degrees of the sun, and this is sort of within 20 degrees. And these 3 different models here are different models of propagation of electrons in the inner solar system. And you can see here that maybe the shape is a little off, although it's within the uncertainties maybe a little hard to tell. But in any case, the prediction of the inverse Compton fairly closely matches the observation. But the same cannot be said of the solar disk. So these two sets of lines here come from the only rigorous calculation of what the solar disk should look like. So this is a calculation done by the University of Delaware group, so Seckel, Stanov, and Geisser from 1991. And they had two basically different models of what the solar disk should look like. So these lines up here show what the sun looks like, assuming that basically there's no additional modulation of the protons in the inner solar system with respect to the Earth, and that basically all protons that hit the sun shower and produce some gamma rays. And this is their prediction for when you take, well, they had a model for cosmic ray propagation in the inner solar system, and this is their prediction with their propagation scheme. These two sets of lines depend on how they propagate the showers through the magnetic fields of the sun. But yeah.
So to get what you're calling currently data here, you take the spatially resolved spectra that you would have on the previous slide, you assume the two templates, and then the spectra are both free but assumed to be universal at all positions.
Yeah, so that is basically how the Fermi team did theirs. So I'll talk about our analysis basically right now. But I just want to point out that the observations lie right here. Spectrally, it really looks like a flat E² spectrum, which was not expected. And it sort of lies between sort of this model is obviously wrong, but this was sort of their best estimate of the Seckel et al.'s best estimate, and it's also in normalization off. And the prediction and the Fermi team's observations did not extend above 10 GeV. And you would really like to look above 10 GeV in order to really see what the spectral shape looks like. Yep?
I would imagine it also depends a lot on what you assume on the distribution of the gamma rays produced. If, for example, all the photons or half the photons can scatter on the way back to the mirror, then you get many more gamma rays.
Yeah. So here they did do a Monte Carlo of where they expected the particles to shower, and so, they did it by Monte Carlo within their framework. Yeah. So I'll talk about that also very soon. You're anticipating, yes. The normalization in their models, the normalization is not free here. At least for their models. It's just they take a couple of ansatzes for the electron, how the electron spectrum changes in the very inner solar system, and yeah. So the normalization is not free. Yeah. Okay. Oops. What? Oh, okay. Sorry. Believe it or not, this is actually the first time PowerPoint has totally up and died on me during a talk. Okay. All right. So the rest of, okay, we're back. All right, so the rest of what I want to talk about is really the solar disk, because that's the thing that now the one calculation does not match the observation. We have a ton more data with Fermi, and we can go above 10 GeV, which is what we really want to do, because clearly those photons are not cutting off by 10 GeV, even in the 18-month analysis. So we want to figure this out. And that also has implications for the neutrinos, which is, what honestly John Beacom, Kenny Eng, and Karsten Roth, who is part of the IceCube collaboration. I think he's the dark matter lead on the IceCube collaboration. That's what we really care about. So we're trying to figure out what's going on in the gamma rays because we really want to have a good prediction for what IceCube should be seeing in neutrinos. Okay, so we took it upon ourselves to download all of the public Fermi data and look for the sun. So what I showed you before only went up to 10 GeV. This is Kenny's map of the sun above 10 GeV. So there are, you can see the sun. This is the fake sun. So again, this is one of these, other points along the ecliptic that we sort of follow along to estimate our backgrounds. And there's no spot at the center here, and there's a nice big spot here. So what we did to look for the solar disk in this data is we cut up the photons into different energy bins. We also, based on the fake sun, had an estimate for the diffuse background, although in our fits for the size of the disk emission, we let the diffuse background float a little bit within the uncertainty based on our fake sun analysis. Kenny had a model for the inverse Compton where he let the normalization float, but assumed that the angular distribution was basically 1 over the angle away from the sun, which is what you expect, but let the normalization float. And then he had only allowed a disk component to live within this inner bin. And so he split it up into angular bins of sort of 1.5 degrees width, and we only looked above 1 GeV, where the PSF of Fermi lies within this sort of 1.5 degree bin.
I'm not quite sure why you allow yourself the freedom to let the normalization of that scattered component, or green component there.
So we could fix it, but it's nice to see what it looks like free because then we can essentially get the inverse Compton spectrum. I mean, empirically estimated and not just fixed by a theoretical model. As I showed before with the Fermi team's analysis, the shape of that spectrum is not exactly where the theory curve lies. So we just thought the most conservative thing to do is let that float as well. So this is what the fit looks like in sort of this 1 to 10 GeV bin. Yes, the inverse Compton does. And then the solar disk only appears in the inner bin. Yes.
Okay, let's say 4 degrees, it's like 2 point something, and 8 degrees, it's 2 point something.
Yeah. Okay, so we also then can go up to, this is sort of the 10 to 100 GeV bin. So for the spectrum that I'm going to show you, we bin it up more finely in energy than this, but this is just so that we have enough photons that you can see. We actually detect a few photons above 100 GeV. I think the most energetic photon is about 300 GeV, but there's only so much you can do with 3 photons, so we cut off the analysis at 100 GeV. This little inset shows you what happens when you bin things up more finely towards the center of the sun. But in any case, we really robustly detect both the disk and the inverse Compton.
So, I'm sorry, if you can go back one again. I mean, I look at the data and it actually looks pretty flat out there. And there must be a degeneracy between that part and what you take as the amplitude of the diffuse background.
Yes, yeah, so there's a little bit of a degeneracy out there. But if this amplitude were, a little too high, then we wouldn't expect the shape to match up quite as well. So we fixed the angular shape of the signal, of the inverse Compton signal, but let the energy normalization float. So there is a little degeneracy, but we can beat it a bit by having two different angular distributions for the two components.
Roughly how many photons is this all based on?
Oh, that's a good question. I should have asked Kenny before, but it's like tens of thousands of photons. I mean, not in this energy bin. There are fewer in this. There are more like hundreds, maybe to up to 1,000 maybe in this bin, but there are many photons. So this is our best estimate now of the solar disk component. So there are a couple of interesting things to point out here. So this is, again, the sort of Seckel et al. Sort of best estimate range. You can see that we're, above here. But you also see that the spectrum is not softening that much at higher energies. But you also see here that we don't actually match the 18-month Fermi data. So what's going on here? Why are we not matching the 18-month Fermi result when we've got 6 years of data that we're looking at here?
And why did you start with GeV?
GeV, just because the PSF we would have had to do a more complicated analysis. We just wanted to do something simple, and we cared most about high energies. So that's why we cut it off, because that's where the PSF is nice and small, and we can get away with a much cruder diffuse analysis than we otherwise would.
Could you repeat where these photons are coming from? The cosmic ray hits the sun.
Yep.
And you get a shower.
Yes. Yes.
But it's mostly reflected cosmic rays off the sun.
Yeah. So I'll show you. So that is true. It's mostly, we think, galactic cosmic rays reflected off the sun, but I'll show you our estimate for the limb component in a second, which will show why. So the other reason why we think that this comes from the disk has to do with this observation right here, that our 6-year result lies actually significantly below the Fermi 1.5-year result. So this is not that we've screwed something up. There's actually something really interesting going on here. So when we do this is the 2-year analysis, not 18 months, but Kenny's also done the 18-month. We actually basically exactly reproduce what Fermi sees when we do the 18-month. This is 2-year. But when we break up our data set into 2-year bins, so this bin here is sort of basically 2009-ish with a little bit of 2010 and a little 2008 in. This is the next 2 years, and this is sort of 2013, 2014. You see that within sort of about 10 GeV, the normalization of the spectrum really goes down with time. And this is within the 1 to 10 GeV energy range, very significantly detected. So in order to assess how significant it is, what Kenny did is we looked at like a fake sun. So again, we have to estimate our backgrounds and so forth. We've got fake sun either trailing or ahead of the sun. We do our full analysis on that. We also looked at the Vela pulsar, which is the brightest gamma ray point source in the sky. And we also looked sort of in the wings of our real sun ROI. And what we find is that for sort of sources that should be, on scales of months or years steady, namely the fake sun Vela or, the outskirts of our ROI, we don't see any time variation in the signal, but within 1 to 10 GeV, the solar disk, we see a very strong time dependence in the data. So,
Is it consistent with the solar cycle?
yeah, so, right. Yes, yeah, so that's exactly, what the timing is very good. So, for that. So, I'll show you more in a second too, but yes. So, it's very closely tied to the solar cycle. We can also unpack the data to make sure that we don't have anything weird going on. Like, one of the things that we worried about is, do we have basically flaring sources in the field that are creating some background for us? Let me walk you through the data. So this is the first 2 years of analysis. So Kenny's bin things in sort of 2-day periods. These are photons above a GeV. You can see that the normalization is starting to go down a little with time, but there are no weird outliers if you look day to day. The normalization is still going down in years 3 and 4, but we've got this like big bump up here. So what's that? So that is that whopping flare that I showed you back when I talked about flares. So we've cut this from our data set. It's very, very bright, clearly, but only lasts for about a day. So actually for this time window, it's less than a 10% contaminant. Okay, and then years 5 and 6, as we're getting deeper into the active phase of the sun, as the sun gets more active, we expect to see more flares. And indeed, this is also a well-known flare. So basically, we've rediscovered some flares, which is good. But for us, it's a contaminant. We want to know what the sun's doing sort of on average, not when we have these gigantic blasts of gamma rays from presumably magnetic reconnection events. Okay, so let's talk a little bit more about this and what it implies for the solar cycle and the magnetic fields associated with the solar cycle. So another piece of evidence that really in addition to this time series data, what's going on is that we can look at what should really be a steady source of photons, namely the limb, where you've got cosmic rays coming in the limb, and they don't worry about so much what the magnetic field looks like. You don't have to worry about mirroring. They just should penetrate a bit through the atmosphere of the sun. That limb, this more steady source, is really low compared to our data, which is another piece of evidence that what we're really seeing is cosmic rays, hitting the solar disk and being reflected out. Oh, so that is interesting. So Kenny has not looked at that yet because we're really focused on the sun right now, but that's definitely... Yeah. So what I've shown you now is this is just in our fit what we when we allow just that inner bin to float. That is basically our solar disk component. So we have not looked at the variation in the inverse Compton. We've just looked at what the fit in our time slices and energy bins.
Would you expect it?
Yes. Yes. Yeah. Why? Because the electrons, so I could maybe get into it more later. I expect it to change a little bit, but not as much as the disk. And the reason we expect it to change a little bit is the cosmic ray electrons get modulated by the magnetic fields in the inner solar system just as the protons do. However, when we're looking for through the inverse Compton halo, a lot of the signal comes from sort of 1 to 2 AU, where the modulation is not as strong as we think has to happen in order for the solar disk to look okay. So we expect to see some variation, but not as strong. Yeah. Okay. So what we think is going on with our time series data is that the cosmic ray protons are getting very modulated as a function of time, tied to the solar cycle. So the sun gets more magnetically active. It prevents more cosmic rays from getting close to the sun. And it happens at actually a really interesting energy point. So a 10 GeV photon from essentially pions has to come from probably something like of order 100 GeV proton. Okay, so that's an interesting energy scale to have in mind. So when we look at galactic cosmic rays at the Earth, we see strong variation with the solar cycle. So this is a nice picture of the corona of the sun taken with the Yoko experiment. And when the sun is very active, namely in the early days of the Pomela mission, we saw a decrement in the protons at the Earth compared to what we expect the local interstellar spectrum to look like. But we see this turnover sort of at GeV energies. Okay, so at Earth, the heliosphere is really affecting things below about a GeV. But what we're seeing in order to give the time-varying signal that we see up to 10 GeV with the solar disk, we really have to be modulating 100 GeV protons, which is way out here.
Are you talking about modulation of the sun?
Yes. Yeah.
You can estimate that.
Yeah. So what we've shown empirically is that there has to be some very significant modulation. And our next step is to try to figure out if we can actually reproduce that with more theoretical calculations. So one additional bit of supporting evidence that what we're seeing is really very severe modulation of the proton spectrum near the sun, and that's what's causing the solar disk component to change, comes from observations of protons, cosmic ray proton anisotropies with the Tibet air shower array. So the Tibet air shower array published a recent paper in which they looked at protons coming from the direction of the sun, sort of at 100-ish GeV to 100 TeV energies.
Are the cosmic rays isotropic with the sun?
Probably not isotropic because a lot of them get, some get absorbed and they also get deflected. But what we see here actually with the Tibet air shower array, so the more orange it gets means that you see a deeper decrement in protons coming from the direction of the sun. What you see is that when the sun is quiet, you see a much bigger, essentially, shadow of the sun, basically from protons, whacking into the sun from behind, than you do when the sun is very active, so around here. And so the hypothesis is that when the sun is very active, the magnetic field structure of the corona is much more complicated, the fields are a lot stronger, and you end up basically scrambling up the cosmic rays. Whereas when the sun is quiet, the magnetic fields aren't as strong, they aren't as crazy, and you're not basically scrambling them up. So the cosmic ray protons have a much straighter trajectory than they do when the sun is active. So what this group did is they actually basically did proton orbit simulations with a couple of different coronal field models, and they were able to reasonably explain their decrement as a function of solar cycle with this magnetic field model in the very inner heliosphere. So that is very interesting, and so that's something that we're following up now with theoretical calculations. We're taking these same models and propagating protons through these fields. Okay, so let me just talk about implications for observation. So we've now observed the sun in GeV with Fermi, but there are a number of really exciting experiments coming up. So HAWK is this air shower array in Mexico, and they've started publishing their first results. They are very excited because, obviously you have to extrapolate basically an order of magnitude here. So I should say the difference in these points here, the blue points up here are just our solar disk measurement, I got that wrong. So the shaded region is our solar disk measurement. The blue points here show all the photons, including inverse Compton, coming within 1.5 degrees of the sun. And so, if you just draw a line through our points here, it suggests that maybe the sun could be a nice source for Hawk. And certainly for LHASA, which is this very ambitious Chinese air shower array experiment proposed for Yunnan province in China. Of course, what we see should actually depends on where the spectrum cuts off. So we do actually expect this to cut off somewhere because at some point you just can't mirror very high energy protons out of the sun because the Larmor radius is way too big. And so at some point we do expect this to cut off. But where it cuts off tells us something very interesting about the magnetic field structure in the photosphere. But it's suggestive that you learn something interesting and possibly see a source of high energy gamma rays in the sun with these experiments. So John Beacom has started talking quite a bit with people in Hawk about that. We also expect to see a neutrino signal, as I measured before. And this is also kind of interesting. So actually we expect the surface brightness of the sun from these cosmic ray interactions to be brighter than the cosmic ray-induced neutrinos coming from Earth's atmosphere. So these few lines here are estimates of sort of the, integrated within the solar disk, what the Earth atmosphere neutrino should look like. We expect the sun should be brighter. So the problem with current searches is that it's concentrated at low energies where you basically get this kinematic smearing of the arrival direction of the muon coming from these neutrino showers. And so basically you soak up a lot of background from these Earth atmosphere neutrinos. Another interesting thing here is that the reason the spectrum is falling so sharply at high energies in this one of the very few theoretical estimates of the neutrinos from solar atmospheric neutrinos is that the sun actually absorbs neutrinos at above about a TeV. So you see a lot of neutrino absorption. That's why this spectrum is not harder. One interesting thing that Kenny's found so far is he's been doing an improvement over the Sekal calculation of how charged cosmic rays actually propagate in the flux tube and tubes of the sun and how those charged particles get mirrored. And even for very high proton energies, you actually see some deflection of the protons away from basically just, straight line trajectories through the sun. They get deflected away. And that's interesting because then those showers see a smaller column and you should possibly get actually more neutrinos out of these interactions because they don't get reabsorbed. Okay, so our next steps are to really do this full solar disk calculation. We're sort of halfway there. We did the limb as a warm-up. And we're sort of partway through this calculation. And then the thing that we're really interested in is neutrinos. And that is also something that Kenny's working on. Okay, so let me conclude. I've talked about the sun as a laboratory for both astrophysics and fundamental physics. However, for the GeV part of this talk, I really focused on the astrophysics, namely cosmic ray propagation and so forth that you can get from looking at the sun in GeV. So I showed you our preliminary new result of the energy spectrum of the solar disk with 6 years of Fermi data, and we can see that our signal goes up to sort of the 100 GeV range. I showed you that the solar disk is actually very time variable, which tells us something interesting about charged particle propagation in the inner solar system, and that's something that we're investigating. And I also suggested that the sun is going to be is potentially a very interesting target for air shower arrays, also for neutrino observatories, but it really depends on where the spectrum cuts off, and that should actually tell us something interesting about the magnetic fields and structure of flux tubes in the atmosphere of the sun. All right, I will leave you with propaganda for my research center. All right, thanks.